So good evening, everyone. My name is Vasista, and I'm the group lead for the Chaos Theory with Machine Learning and Neural Networks group with the Dr. Akul Lab. So basically, what we're trying to do is we're working on revolutionizing classical mechanics with the use of machine learning. We're currently working on predicting the motion of chaotic systems using neural networks and other machine learning techniques. So first off, what even are chaotic systems? So chaotic systems are dynamical, highly unpredictable systems that are very sensitive to initial conditions. So to predict the motion of these systems, we use chaos theory. So using calculus, we can create differential equations to predict the state of the chaotic system at a given time. We also focus on the underlying patterns as well as the deterministic laws. But in the end, predicting the motion involves machine learning and neural networks, like we continue like in our group today. So our current project, we are currently focused on the multi-pendulum system. The multi-pendulum system is one of the most well-known chaotic systems, and it's basically just one pendulum attached to another. And a slight change in the initial angles, theta 1 and theta 2, for the double pendulum results in vastly different movements of the two pendulums. And our goal is to predict the motion of the double pendulum as well as the triple pendulum. So here are the differential equations. So to solve for the movement of the two angles with the double pendulum, we need to solve these differential equations. We have not made a visualization for the differential equation to solve a triple pendulum, but we have it for the double pendulum right now. So what are the applications of this research? Well, there are applications in the aviation industry. So being able to predict the motion of chaotic systems such as wind can result in climate prediction for more effective flight planning, as well as a reduction of delays and cancellations, forecasting electric power load of a flight, which will also save energy, and aviation accident prediction, which has shown chaotic characteristics in the past. There are also industrial applications, so more efficient airplane wings, better power delivery systems, more efficient and possibly more powerful turbines, more efficient chemical reactions in industrial plants, as well as increasingly good conveyor belts for factories. There are also healthcare, as well as some other general uses. So it's possible that we can have implantable defibrillators. We can also have artificial brain pacemakers. We can also have artificially stimulated chaotic brainwaves that could help inhibit epileptic seizures. There's also been a past example of satellite control, such as with the International Sun-Earth Explorer 3 back in 1978. And of course, there's predicting the stock market, as well as some human convenience applications, such as more natural air conditioning. And with that, I pass on to Sabrina to talk about our initial progress.
I'm Sabrina, and I'll talk about our initial progress. So far, we use the Runge Kutta Method, also known as the RK4, which are the differential equations we use to calculate each angle. We use this to solve and create an animation to model the double pendulum, which I'll show the animation later. And we also use this Runge Kutta method to solve the triple pendulum and analyze the movements to see if we can spot patterns of chaotic motion. We also implemented the impact that friction will have on double and triple pendulums. And currently, we are predicting the movement using LSTMs, which are a type of deep recurrent neural network that is specifically good at modeling long-term dependencies. So far, we have a few machine learning models we use to predict the double pendulum. Some models we programmed are the linear regression model with the implemented polynomial feature map. And basically, this feature map uses the original data and turns it into a new set of data with higher dimensions. And the random forest regressor, which basically combines decision trees into a single model, and also the multi-layer perception regressor, which is a model that can map one space into multiple dimensions. We also tried out neural networks to improve our performance, and we use both recurrent neural networks and convolutional neural networks. And the RNNs we used are LSTMs, the vanilla RNN, the bidirectional RNN, and the stacked RNN. The CNNs we used were the feed-forward neural network and the gated recurrent network. The metrics we use to evaluate our models' performances are R squared, which is the coefficient to measure how well the model fits the data, and the root mean squared error, which basically measures the error between the predicted angles and the actual angles. So this is our code for the solution to the differential equations. We use Python. Yeah, and these are some of our graphs with the differential equations used. And this is the animation of the double pendulum we coded.
Hello, my name is Sude, and I'll be talking about the model analysis and the predictions that we've done so far. So we've started with random forest and linear regression, as they're the most simple machine learning techniques that are usually used in problems like this. And these methods actually provided pretty satisfactory results, but we saw an even better alternative, which was using neural networks, and that even greatly improved our performance in predicting these pendulums. And so, yeah, so building on the existing research, like about the double pendulum and chaotic systems using neural networks, we started using RNNs, which were known to be like one of the best neural networks for predicting these non-linear time step problems. So we used LSTMs, again, vanilla RNN, bidirectional, and stacked RNNs. And again, yeah, like Sabrina said, we use convolutional neural networks. And we added one extra machine learning model, which was the multi-layer perception regression. And this progression from the basic machine learning to the advanced neural network architecture has allowed us to push the boundaries of what is possible in analyzing chaotic systems like the double and triple pendulum, and demonstrating that neural networks have the potential to significantly improve predictions in these nonlinear time steps. Yeah, so these are our machine learning model accuracy numbers. So as you can see, for random forest, starting off, we already have pretty good results. We have an RMSE of around 0.01 and an R squared of 0.98. And it only gets better from there. Like for linear regression with a polynomial feature map with the power of 2, we got 0.999 for R squared. And our best machine learning model was the MLP regressor, which went to 0.9987, and that was, out of the 3 that we tested in machine learning, that was our best model. Now shifting to neural networks. As I talked about, neural networks really changed the game. Starting off with LSTM drastically improved our results. We got 0.9 and then 7 nines and a 5, which is really impressive. And our lowest R squared of 4.7 to the power of -5, so times 10 to the power of -5. And that was our best neural network so far. And continuing on with the vanilla RNN and the stacked RNN, both of them had, again, pretty satisfactory results, as you can see on the screen. Lastly, we go on to our convolutional neural network and our other different models. So our best convolutional neural network was the feed-forward neural network. And surprisingly, it gave an R squared of 1, but the RMSE wasn't as great as the LSTM. But that we might have to do a little bit more work on that, but it looks really promising. And the feed-forward neural network and the LSTM are both right now our best models for predicting this. And the gated recurrent network and the autoregressive model were two of the other models we tested. They both also gave satisfactory results. So almost every model we've tested so far has given us great results, if not like amazing. And this is a visualization of our actual angles versus the predicted angles for the when theta 1 is 60 degrees and theta 2 is 90 degrees on the double pendulum, that is. So you can see how it almost lines up perfectly, the actual theta 1 and the predicted theta 1. Same for theta 2. They almost line up exactly, showing how accurate our models are, at least the LSTM. And same for feed forward, although this was different initial conditions. Again, we can see that it almost perfectly lines up because we have very high accuracy on both models. So these are our two best models for this problem. And lastly, here we have training vs validation loss. It looks pretty good, but we have a slight concern about the fluctuations in the validation loss, and we'll have to look into that. But overall, it seems okay for now. Yeah, so this is our triple pendulum models now. So far we've only have three models for our triple pendulum, which is the autoregressive model, a gated recurrent network, and the linear regression with the feature map. We're currently working on getting more models as we have a separate team working on the triple pendulum. But again, here linear regression was our best model so far. We still have to go deeper into the triple pendulum because we've only had 3 models. But yeah, that's our triple pendulum models. And on the next slide, we see our predicted vs actual again. It almost perfectly lines up. The first graph is theta 1, which, as you can see, you can't even see the blue line because that's how perfectly lines up. Same thing for theta 2 and theta 3. Our linear regression has done surprisingly well with the feature map, and we're looking into improving that even more with some hyperparameter tuning and the other techniques. And we'll go into more models and update from there. So passing it to Asista for future plans.
Yeah. So as you can see, we've had a lot of highly promising results. So as for future plans, right now we want to test our models for all of the initial angles. So in each of our models, we've only been testing or training these models on only one set of initial angles, but this isn't sustainable. And what we want to do is we want to make it so that a single model trains on data from all of the different initial angles, and this would give us a more comprehensive overview and make us truly understand how good our models really are. Second thing is we want to continue with our triple pendulum models. So with the double pendulum, we've kind of understand how we need to approach with the triple pendulum and in the future with other chaotic systems as well. And so we expect triple pendulum progress to go fairly quickly. And yeah. The third thing is we do need to find a few more models and papers for comparison. This is just to make sure that our results are novel and to also let us see where we can improve and where we can explore places where there hasn't been any work done before. Fourth thing is we want to do all these models again with the aspect of friction included. I think that this should be pretty simple because we have narrowed down which models are the most accurate, and so we would do these models again for the for including our friction, and we would show our findings then. And lastly, we would find applications for the chaotic systems that we have models for. So we would use our knowledge from the double pendulum and the triple pendulum to kind of expand into the applications that we were talking about earlier in the presentation, and this would really give us some more real life impact of this research. Yeah, and that's our sources. And thank you. Are there any questions?